In this system, we shall see classic power amplifiers further. Now, in the last video, we have seen the circuit diagram of the class A power amplifiers using the MOSFET. So this M2 and this transistor will going to form the current source, which is allowing a current of I to flow through this power amplifier. As you can see now, this MOSFET M1 is always having a DC current of I, which is flowing through this. The AC current will going to flow through the resistor RL. Now that means to say the M1 transistor is biased such that even if the input voltage is 0, there is a current of I flowing through the M1 as well as M2. Now we know that V0 is given by V in minus of VGS1. So this is what we already seen. So let us have a look at how does the output waveform looks like and what is the VDS of this M1 transistor. We know that as the input voltage varies, the output voltage follows the input voltage with a small difference of VGS. Neglecting this VGS, so we can approximately write V0 is equal to Vin. So in the next slide, we shall see now, you can see the output voltage is varying from 0 to VCC and it is going up to minus VCC. So this is VCC taken, considering it as a transistor BJT. Now for MOSFETs, we can take it as this is VDD and this as minus VSS. Now you can see output swings from plus VDD to minus VSS. The peak to peak of the output voltage is 2 times the VDD. Now you can just have a look at what is this VCE1, which is exactly equal to VDS1. So we know that VDS1 is nothing but, so this is the VDS1, which is nothing but VDD minus V0. So when V0 is 0, VDS1 is actually VDD minus 0, so which is equal to VCC here. So this is what is VDD. When the output voltage is 0, the VDS1, so this is VDS1 is equal to VDD. So as the output voltage increases, because the output voltage is nothing but the variation of the output voltage with respect to input. As the output voltage increases, now the VDS1, so as this voltage increases, the VDS1 will reduce. So that's what is happening here. So as output voltage increasing, this VDS1 is reducing. So this goes to the minimum of 0. So when the output voltage is plus VCC. Now again, when the output voltage goes to minus VSS, that is minus VSS here, the VDS sat, that is the VDS of this M1 transistor will become 2 times the VDD. So why it is becoming 2 times VDD is, now the output voltage here is minus VDD, here it is plus VDD, the difference becomes 2 times VDD. So this is how the variation of VDS1 of the M1 MOSFET varies as the output voltage changes. As you can see now, the maximum drain to source voltage across M1 is 2 times VDD and the DC current flowing is I. So naturally the MOSFET which is used for power amplifier should be capable of dissipating very large amount of power. So instantaneously for a very small duration, the amount of power it has to dissipate is 2 times this VDD multiplied by I. So that's why it was said in the beginning that all power amplifiers should have power transistors for their operation. Of course, we have seen the class A amplifiers have a very poor power conversion ratio, that is like 25% theoretically, so that's what is we proved here, and typically it is around 10 to 20%, and it is also concluded that it is not used for high power applications. Now we should see is there any possibility of modifying this class A power amplifiers to get a better efficiency. Let us have a look at this transformer. So as you all know that the transformer won't have a primary and secondary windings. So let us assume that on the primary side we have V1 as the primary voltage, I1 is the primary current, N1 is the number of turns on the primary side. Similarly on the secondary side. So we know that power at the primary side is equal to power at the secondary side, which is nothing but V1 into I1 is equal to V2 into I2. And we also know that V1 by V2 is equal to number of turns in the primary to the number of turns in the secondary. So we can also write the ratio of currents I1 by I2 is equal to N2 by N1. So let us take this V1 by I1. So I'm just retaining this V1 by I1. I'm just multiplying divide by I2 and multiplying dividing it by V2. So there is no modification in this equation. Please rearrange this particular multiplication division of I2 and V2 onto V1 I1. So let us separate this V1 by V2 as one term, the I2 by I1 as another term, and V2 by I2 as the other term. The same equation is being rewritten in this form. Just have a look at what is this V1 by V2. So V1 by V2 is nothing but N1 by N2, and I2 by I1 is also N1 by N2, and this is V2 by I2. Now what is interesting to see here is that V1 by I1, which happens to be the input impedance, which is V1 by I1. So input impedance is equal to V2 by I2 is nothing but the output impedance. So we can certainly relate the input impedance and output impedance of the transformer by its turns ratio, meaning the input impedance is given by N1 by N2 square times uh, square into output impedance. So if you're connecting some output impedance here, if you see from the input impedance, so it will not be only this impedance, it is multiplied by N1 by N2 ratio, or square of that N1 by N2 ratio. That means to say, if we are connecting the resistor RL over here, its input impedance RL dash, looking at the input terminal here, looks like N1 by N2 whole square into RL. Even if RL is small, RL dash looks like a very big value. So this is the main advantage of using these transformers, so which is in the impedance matching purpose. So a very small impedance at the secondary will look like a very heavy impedance at the primary side. So this concept is used in the transformer coupled power amplifiers, because usually the load that will be connected for a power amplifier is very small, so that load will look like a very high impedance on this side. Let us have a look at how does a transformer coupled power amplifier looks like. Now this is a MOSFET M1 M transistor, and you can see we have R1 R2 which is used to bias the MOSFET so that for the entire input cycle this conducts. And we can see now at the load we have this transformer, and there is a load in the form of a speaker connected here to the secondary. Let us see what is the output. Input waveform is varying from 0 to VCC, 0 to VDD in this case. If you can carefully observe here, the output is varying from actually 0 to 2 VDD. Even though the input voltage from 0 to VDD, because of this transformer, so due to the counter EMF effect of the transformer, the output signal will swing from 0 to twice the VDD, twice the supply voltage. Now half of the supply, half of this peak is due to this VDD, another half of the peak, which is the VDD is due to the back EMF produced in the transformer. So that's why the advantage of having a transformer is that the output voltage is actually twice the supply voltage. Even though supply voltage is 5 volt, you can able to get a peak to peak of 10 volt here. So it is purely because of the counter EMF effect which is being generated in the transformer. So let us have a look at what is the power conversion efficiency of these class A transformer coupled power amplifiers. Now we know that the power conversion efficiency eta is given by the power delivered to the load divided by the power being consumed, power being drawn from the power supply. So as we know that we have only one power supply now, that is VDD, and we are assuming a current of I flowing through the MOSFET. So the power that is drawn from the power supply is voltage into the current, that is VD into I. So we shall have a look at what is the AC output power, which is nothing but VRMS into IRMS. We know that VRMS is equal to V peak by root 2, and IRMS can be written as I peak by root 2. So multiplying these, so V peak is nothing but VDD and I peak is nothing but I. So the AC power, which is the power delivered to the load, comes out to be VD by I. So we know that power drawn from the power supply is VD into I. So efficiency becomes substituting these values of PL and PD happens to be half, meaning the efficiency now becomes 50%. You can see the advantage of going for this transformer coupled. It's again the same power class A power amplifier. Now the efficiency is increased by 2 times. For a class A amplifier with a resistor was found out to be 25%. Now it is using this transformer coupled configuration, we can able to increase the efficiency to 50%. So this is the biggest advantage of going for transformer coupled power amplifiers.